Okay, well, welcome. This is going to be part two of our lecture. I guess I showed you the answer, but that's okay. What I want to do is I want to solve this problem here. And the motivation for solving this problem comes from the last lecture where one of you asked me, if you're doing a titration and you're somewhere in the middle of the titration, how do you calculate the pH? And so that's precisely the problem that I've created right here. We have a certain volume of a certain concentration of ammonia, a weak base, is being titrated with a strong acid, 0.74 molar HCl. What is the pH of this solution after the addition of this volume of HCl? And we're given a Kb value for the base right here. So let's actually go ahead and solve this two different ways. I don't think it's going to hurt at all to see these two solutions. So let's see, I'm dealing with a titration. Again, I've got a weak base here, I've got a strong acid. One of the things that we've learned is that, of course, weak bases and strong acids essentially react completely with each other. And we've calculated equilibrium constants that prove that point, but we can also just memorize, again, the idea, weak base, strong acid, complete reaction. So I can just calculate the number of moles of NH3 and the number of moles of H plus and just let the materials react completely, because that's what's going to happen. So the number of moles of NH3 is going to be given by, let's see, the volume, or volume times concentration. Well, this is an easy calculation. So I've got 0.62 liters times 1 mole per liter, and this gives me 0.62 moles of NH3. And for the H plus, and of course I'm just saying H plus, we added HCl, but it's a strong acid. So if I have this concentration of HCl, I really have this concentration of H plus, as we know very well. And so let's see, the volume is 0.3 liters. So I'm going to take 0.3 liters and multiply that by 0.74 moles per liter. That kind of looks like a 9, but it's not. It's a 4 right there. So let's see, we take 0.3 times 0.74, and we get 0.22. And I guess we could kind of be a little bit official and formal about this, and we could say, well, what chemical reaction is taking place? We have ammonia that's reacting with H+, that's making, of course this is an equilibrium, but it's going way to the right. So again, ammonia plus H+ is giving me an H4+ right here, and we can run this in a BCA manner, as we should, because we know these are going to react as much as they can. So I've got, and this will just be in terms of moles here in this table, I've got 0.62 moles of ammonia initially, I've got 0.22 moles of the H+ right here, I have none of this, and so we're running our little BCA table. And I'm going to let, so I recognize that this is the limiting reagent. All of this can react, and I'll still have some of this left over, but I certainly don't have enough H+ to react away all of the ammonia. So I'm going to let minus 0.22 moles of the H+ react. That means that minus 0.22 moles of the ammonia react. This gives me 0.4 moles of the ammonia left. It gives me 0 of this here. I get plus 0.22 here, and I get 0.22 here. So how do we solve this problem? Well, there are two ways to solve it, and we could use the Henderson-Hasselbalch equation, or we could just set up an ICE table. I don't know, let's start with the Henderson-Hasselbalch equation. So what we're really saying there is that we have ammonium, that's acting as a weak acid, dissociating to form H+ plus NH3. So the Henderson-Hasselbalch equation was formulated based on some kind of a weak acid. And we remember the formula is pH is equal to pKa plus the log of the conjugate base divided by the acid. So let's throw in some numbers right here. Let's see. Oh, I don't have a pKa, or I don't have a Ka for that matter. I just have a Kb. But I know how I can go from Kb to Ka. And so Ka times Kb is Kw. And so let's see, we have 10 to the minus 14. And I'm going to divide that by 1.8 times 10 to the minus 5. And I get 5.56 times 10 to the minus 10. Okay, so let's see, how do I do this? Well, this is going to go here, and I'll take the negative log of it. That's what the p means right here. What about the base? Well, let's see, these are not in terms of concentrations, and technically I should work in terms of concentrations, but what I'm going to do is right here I'm going to take 0.40 moles and divide it by the volume of the solution, and right here I'm going to take 0.22 moles and divide it by the volume of the solution. And this is one of those rather rare situations where technically I could have worked in terms of moles because the volumes are going to cancel here. When I have a concentration over a concentration and they're coming out of the same solution, the volumes will cancel. So they do. But again, if you want to be right all the time, always do your equilibrium calculations in terms of concentrations. But let's stick in these numbers. So we've got 0.4 divided by 0.22. I'll take the log of that. And now I'm going to take, let's see, 5.56 times 10 to the minus 10. And I'll take the negative log of that. I'm going to add these together. And I get a pH for this solution of 9.51. And maybe we could solve this on the same kind of sheet of paper here. Again, the computer only has so much memory or whatever, and the numbers and the letters start to get a little angular, but I think we can do this. Let's solve it a little bit differently. Let's say we've got NH3 in solution. And so we've got a weak base, and let's write out now the expression for Kb, the chemical expression that corresponds to this equilibrium, this K value right here. And so we've got ammonia acting as a weak base. Every once in a while it will pluck off a proton from water. It gives me ammonium plus OH minus here. Let's see, what are my concentrations of my species? Now we should probably actually do this in terms of concentration. So I've got 0.4 divided by what's my volume? Well, my volume is 0.62 plus 0.3, so 0.92. So I have 0.4 divided by 0.92, and that means that my concentration right here is 0.435. And let's see, what about the ammonium? Well, I've got 0.22 moles of it, and I'm going to divide it by, again, the total volume, which is 0.92, and this is 0.239. And this is a weak acid. It hardly does anything in water. This is a weak base. It hardly does anything in water. So the concentration of the hydroxide is going to be pretty small. It's not like either of these is going to go into solution and really react. So we're probably pretty close to equilibrium. Let's run an ice table. We've got our ice. Let's see, we're going to have minus x, plus x, plus x. It's the same game we've played a dozen times, actually dozens of times. And we know what's going to happen here. I'm not even going to write these down. It's just this minus this, this plus this. We're going to neglect x. So we have Kb is equal to 0.239 times x, which is the hydroxide ion concentration, divided by 0.435. And now let's do a little bit of math and solve for x, the hydroxide ion concentration. So the hydroxide ion concentration is going to be, let's see, it's going to be Kb, which is 1.8 times 10 to the minus 5 times 0.435 divided by 0.239, and I get 3.28 3.28 times 10 to the minus 5. I'm going to find a pOH value. I guess there's not a lot of room left here, but I'm going to find a pH value, and that will give me, I'm sorry, a pOH value, and that'll give me a pH value. So I'm going to take the negative log of this, 3.28 times 10 to the minus 5. So I take the negative log of that, and then I subtract from 14, and I get 9.51. So we get the same answer either way. So this is how this is the pH that we got when we ran the Henderson-Hasselbalch equation. This is the pH that we get when we run the ice table. But the point of all of this, again, is we're doing a titration. We're somewhere in the middle of the titration. How do we deal with the problem? And my recommendation is figure out how many moles you have of both species, let a complete reaction occur, and then stick this into equilibrium expressions or use an equation that we've worked with before, and then this should give you the right answer. And in fact, we found it in 2 different ways. So I think that this probably is certainly used up all the time and perhaps a little bit more. So I wish you luck in preparing for the test and all that. We'll talk to you later. Bye.